Hi, this is going to be a video breakdown of how we made the robotic arm in Hackspace for a small competition within our course. The objectives of this project was to gain an introductory understanding of the complexities required when building robots used in robotic surgery. All the mechanical processes, such as the type of joints needed, the degrees of freedom, and the actuation, were all considered in our project. The criteria was to ensure the arm had a reach between 200 and 400 millimeters, and was designed to pick up a maximum weight of 150 grams within that range, which would then attach to the electromagnet claw part of our arm. Here was the basic functionality. Underneath this base plate was a servo motor that allowed for panning movement. To allow the tilting of the first arm, we use a second servo motor, and to allow tilting of the second arm, we use another servo at this joint. And finally, the electromagnet, which attaches to the weights we had to carry. The first step was the ideation phase, where we brainstormed the initial designs and put pen to paper, or in our case, Fusion 360. We modeled practically all the components here, such as the base mount, and I actually chose the specific part because we ended up modifying this to include two motors for reasons I'll expand on later. But in our original design, we opted to use steel ball bearings, which I thought was cool as it allowed for frictionless movement. We also decided to laser cut acrylic for the last joint as it was lighter and still maintained its sturdiness. Another optimization was utilizing gravity for the electromagnet joint, as we knew it had to face down anyway to pick up an object, so there was no need to add unnecessary stress by adding an extra motor. In summary, we had to consider the weight, the reach, the stability and stress on each joint, and its feasibility. The prototyping phase was where we really learned about the flaws in our design and provided the most feedback that featured in our final build. Our most prominent first failure was realizing that the first tilt motor was just overworked and it kept on stalling, which actually ate into the servo horn, a problem known as servo linkage wear. We had to reconsider the weight distribution and the supports, and we finally decided to go for a dual motor setup because we could easily include it into our design, and it essentially doubled the stress this joint could tolerate. The only thing to consider, however, was the syncing of the two motors via the code. Even if they were slightly out of sync, it would begin to eat into the plastic link once more. The coding was straightforward but quite fiddly. We set up and initialized all the motors and its input controllers. We then used a map function to normalize the inputs, converting the input ranges to a standardized range. We also made a change to the claw action of the electromagnet because we didn't want to hold the button. The button wasn't very reliable, so instead we modified it to be a toggle on or toggle off functionality. So when it comes to the final analysis of our design, our strengths were that it was incredibly compact, it was stable, versatile, and it provided plenty of degrees of freedom. However, we should have strived for a larger range of our arm, learning that it's good principle to always outperform the requirements by some margin. The reliability of the electromagnet claw function had to be improved. There were some bugs and it led to inconsistent gripping of the magnet. We also had some issues with the motor's short circuiting, which, with more time, we could have sorted out with better wiring, alongside fix the bugs in our code. And with more access, we could use motors with greater torque, and with the extra time, we could create a more optimized design that follows well-documented papers on this topic. But overall, it was a lot of fun, and I look forward to spending more time in Hackspace and doing similar projects like this.